to feed off of what Gail started on Monday. And today I'm going to be focusing on a few more technologies, but mostly some additional strategies for buildings that are especially efficient, and also starting to think about building systems, MEP systems, mechanical systems in the greater context. So how they're influenced by the building and vice versa. So I'm going to jump right in and go through a couple technologies. So the first one, oh, we're still getting some feedback, so just make sure everybody's muted. But in big picture, we're looking for more efficient systems. We're looking for waste recovery or energy recovery, and we started to talk a little bit about that last week when I was talking about the DC water headquarters building and using heat recovery from the sewage lines. So we're looking for waste energy recovery, energy storage, trying to make buildings especially simple, more space efficient, and at the bottom line, trying to get buildings that are better designed for passive operations, and really holistically looking at the whole building as the mechanical system. So I'm going to jump in with one of my favorite technologies, which is old. It's actually predates air conditioning and looking at evaporative cooling. So this is a strategy where we can actually cool air by adding moisture. And so there's in one of our thermodynamic rules, we can't add energy or subtract energy from an airstream. But all of our air mixtures around us in the room that you're sitting in right now has some portion of that energy is temperature, like the sensible heat that you can feel, like hot, cold, and a portion of it is the moisture energy. And in order for that that total energy or total enthalpy to stay the same, if we add moisture or subtract moisture, it's going to change the air temperature because the total amount of energy has to stay the same. So evaporative cooling works especially well in drier climates. And what happens is there's two methods. We can actually add moisture directly to the airstream, and that's going to directly cool the air sensibly. And then so the air coming out is going to be more moist, but cooler. Or if we're concerned about that air getting too moist or too wet, we can use what's called an indirect evaporative cooler. And that has two airstreams. The first airstream is the one that we're trying to cool down. And we run that through a heat exchanger that we're pulling a second airstream through. So this diagram in the lower right hand sort of indicates that we have a second airstream, and that's the airstream that we're going to add moisture to. So that secondary airstream is going to get cool. And as it passes through the heat exchanger, our warm air is then cooled by that second airstream. So we get the effect of cold air without adding moisture to our primary airstream. We really like these strategies because they're low energy and there's no compressor cooling, which is really exciting because that means they don't use very much electricity. They do use water, obviously, and in a drought condition, you might be concerned about that. Although, if you're using evaporative cooling in lieu of traditional air conditioning, there was a recent study at UC Davis Western Cooling Efficiency Center that compared the water usage of electricity versus the water usage of evaporative cooling. And evaporative cooling uses less water than using electricity for air conditioning because the power plant that the power is coming from also uses quite a bit of water in general for most of the Western United States.
You need to mute everyone.
Again, everyone, just please mute yourselves. If you have a question, go ahead and use the chat window, and we'll try to respond. So this is just another diagram of sort of more sophisticated of those of the two schemes. So the image on the left is a direct evaporative cooler, and the image on the right is the indirect evaporative cooler. I've used both of these in projects pretty successfully, even in the Bay Area. One of these is actually not too far away, just over the hills in Orinda. So this is the Orinda City Hall building. This was probably built, oh gosh, maybe 12 years ago, 13 years ago. But it was a project I worked on. And Orinda actually gets pretty warm compared to Berkeley and Oakland. When they, if you can go visit that sort of over the hills, you'll notice that the temperatures in the summertime can easily get into the 90s and sometimes peak in the low 100s, which is pretty warm to not have normal traditional air conditioning. But this is a Siegel and Strain project. They were the architects. Just notice on the sort of southwest facade, there was a pretty concerted effort to go to a lower window to wall ratio, but areas on the lower level that really did need more daylight have pretty deep shading, both horizontal and vertical. So you can actually start to see some elements of your shading designs from your projects. So there's a deep overhang, but you can also see here some vertical elements. And then on this other facade facing a little bit more westerly, again, deep overhang plus vertical fins to help with the shading. So a lot of effort to bring down the loads, make the cooling loads low, so that you can use evaporative cooling for the project. So another technology that we get pretty excited about is the use of chilled beams. And so I don't know if folks have heard of chilled beams or ever worked on a project with them, but it's not a structural thing. I think that's one of the biggest confusion marks is people ask, oh, it's a structural piece that gets cold. It's not. It's just the name for it. But I'm going to quickly just sort of walk you through how we use chilled beams and how they can provide cooling to the space. So on Monday, Gail talked about separating ventilation systems from heating and cooling, where we have like a DOAS system, dedicated outdoor air, that just provides ventilation air to the space. And then we have some other element that's providing the sensible heating and cooling to the space. So chilled beams are an example of that. So what we have for chilled beams is we actually take that ventilation air that the DOAS system is delivering to the space, and we push it through this little box. And the blow up here in the middle is kind of an illustration of what that box looks like. In the red area, the air is sort of blown into that red portion and pressurized, and then it's shot through nozzles at pretty high velocity out into the room. And what that does is it actually causes a force called induction, which is represented by these little red arrows coming up from the middle. So, and I'll talk a little bit about this in the next couple of slides, but the idea is that by blowing high velocity air through these fins, you can actually draw air from the room over your heating or cooling coil, which are these sort of striated elements shown. We love chilled beams, especially for lab projects or other high load spaces, because we can get a lot of cooling and a lot of heating out of a relatively small system. You can actually, in the image on the left, you can actually see a chilled beam. It's this sort of piece next to that column. You'll see a little grill and a little slot that the air blows out of, but very sort of reserved. It's not very noticeable. It's a pretty shallow element, but it allows us to do all the fun things that we love about decoupled systems. So low energy use, especially low energy use. It can use mild temperature water and save quite a bit of energy on the overall project. So I want to go in and actually talk a little bit about how this idea of induction works. And it's actually very similar to some vernacular architecture from Appalachia. So I don't know, I can't remember if anyone in the class is from sort of the Appalachia region, or the sort of the southeast portion of the United States. But if you look at vernacular architecture in that region, a lot of early cabin designs were built with what's called a dog trot. down the middle. Essentially, it's a breezeway. So this opening in the cabin going through the middle is a breezeway. And they were designed because they didn't have air conditioning, but the area was still hot and humid. And one of the few ways to actually get to a to be comfortable in a hot, humid climate is to try to increase airflow, get higher velocity air across the body, across the skin. And so the dog trot is a way to actually induce higher speed air than you would get from the prevailing winds. And there's two sort of physics ideas, both from Bernoulli and Venturi, that sort of explain the two things that are happening that make this work really well. So here's just an illustration of what's going on. If you have a steady airflow and you constrict the space that it has to go through, but the mass flow rate stays the same, Venturi is going to tell us that the speed is going to have to increase. So if you have a smaller orifice, a smaller restricted space, and you're trying to push the same amount of air through it, or fluid, it has to increase in speed. And then what we know is from our Bernoulli equations from fluids is that once you have a higher velocity flow, you're actually going to get a lower pressure. So the pressure within that space is actually going to drop as the velocity increases. And so we can actually take advantage of those two factors when we look at chilled beams. So that those nozzles sort of shown on the right, you can see the fresh air, the ventilation air is blowing really fast through there. And when we have very fast moving air, it's going to create a low pressure zone. And that's going to actually draw air from the room to try to fill that low pressure zone. So air from the room is going to get sucked over the heating or cooling coil, sort of that thing in the middle, sort of right here. And that air is trying to fill in the low pressure zone that's caused by those Venturi nozzles. And so it's a really effective way to use your ventilation air to actually mix a whole bunch more air in the space. So rather than having a normal diffuser, Gail showed a bunch of diffuser styles on Monday, instead of having a normal big diffuser that's designed to mix a whole bunch of air in the space, this is using just a little bit of air and using natural sort of laws of physics to suck air from the room over these coils. So we use chilled beams all the time. We have two projects right now up at LBNL, up at the lab, that use chilled beams for labs. So they're a really effective system. They're very quiet, but they work especially well. They come in two varieties. You have active chilled beams and passive chilled beams. So active chilled beams are the ones I've generally been talking about, where you've got air, you take your ventilation air and blow through them. But there's another class of chilled beams that have quite a bit less capacity, but they're called passive chilled beams. And in passive chilled beams, they're predominantly only used for cooling, but they rely on the fact that cold air wants to sink from buoyancy. And so it takes a large or a relatively tall channel, and as the cooling coil activates and it becomes cold, air hits it, gets cold, and wants to sink, and that forms sort of a suction, if you will, on the backside, and so air from the room is pulled in to make up that air. Like I said, it's just buoyancy driven, so they tend to have quite a bit less capacity. So the next system we're going to talk about, Gail already introduced, so radiant heating and cooling. This is probably one of my favorite systems, and I use it in as many buildings as I possibly can, including my own home. Very effective, very comfortable, and I'll talk a little bit about how we can use radiant cooling specifically in sort of really innovative ways. So Gail already sort of talked about the systems, essentially taking an entire surface in the building or multiple surfaces, so ceiling, a floor, sometimes even walls, and embedding tubing in those so that they can become actively heated or actively cooled. I love radiant cooling. It's exceptionally comfortable without the drafts that are typically associated with all air systems. And you can actually, when you have cool surfaces around you, you can actually tolerate warmer temperatures because the mean radiant temperature of the total space, the operative temperature, is still within the comfort range, even if the air temperature is a little bit warmer. And you can sort of think about that relationship when you're sitting at the beach on a relatively cool day with cool breezes coming off of the coast, but you're very warm sitting in the sun, like you're getting all that radiation from the sun. So that's the mean radiant temperature sort of overcoming a lower air temp. Well, the same phenomenon can work in reverse with the space being a little bit warm, but cool surfaces all around you can give you the sense of coming into a much cooler space. And Gail showed a couple different installation types. So we really like embedded systems where we're in some sort of mass, the concrete slab, because it gives us ability, like I mentioned in the innovations lecture, on load shifting. We can actually change when we provide the cooling to the slab and still get the space to be relatively comfortable. Of the two system types, we use both. So thermally active slabs, I just talked about, but we also have quite a few projects where we do radiant panels, especially if there's a concern about flexibility in the future. So a radiant panel can be taken apart, moved. You can add additional ones if you need more capacity or take some away as the program changes. So in some project types where the program is going to churn a little bit, we might bias towards panelized systems to provide more flexibility. Here's just some images from the IDEAS office, or the Integral Group San Jose office, which has an active mass radiantly cooled slab. And one of our former GSIs on a research trip, Katie Ackerley, who now I work with. She's an architect now at David Baker. So she and I work together all the time. But you can see the body heat and the cup of coffee heat shown in this false color imagery, but you can see that those cold surfaces on the floor. So the floor is actively absorbing that energy. Radiant cooled slab floors actually are very effective at also capturing direct sun. So if direct sun comes into space and hits the slab, that energy is nearly completely absorbed right into the slab in the cooling system rather than dispersing in the space. So radiant cooling systems are actually quite effective at dealing with direct sun, more so than we probably thought even 5-6 years ago. So I want to talk a little bit about a recent project that I've got. This is the Teaching and Learning Center at UC Davis, and I can't remember if I mentioned this project before in this class, but this is under construction. It's a new general ed classroom building. And one of the key elements of getting this building to work and using radiant cooling was actually making sure that we effectively reduced our solar loads. So again, from an integrated design standpoint, we want to make sure that we're cutting down the cooling load as much as possible. So you'll notice a relatively restrained window to wall ratio, lots of deep shading, both for the large canopy on that south facade, but also in the individual windows in the classrooms. You'll notice both vertical and horizontal shades. So not all that dissimilar from your shading project. We have both vertical elements and horizontal elements and light shelves inside, and then a large canopy element for the outdoor study spaces. So how we got the loads down, I'm going to sound like a broken record, and I'm sure you guys are sick of hearing me, but facade matters, the facade matters. So besides the really good shading strategies, both vertical and horizontal elements, and also setting the window really back into this deep wall, we also have a very high performance wall. So notice that we're using the thermally broken Cascadia green girt clip systems with exterior mineral wool insulation plus interior wall insulation. So a very thick assembly, lots of insulation, a good rain screen design, and really good solar control. All of those things work together to actually allow us to really reduce how much of the ceiling would need to be covered with radiant panels. So it's not often in this class that we show mechanical drawings, but I thought I would. In the image here, you can actually start to see each of the radiant panels laid out and the piping that goes to each one of them. But the key thing is radiant ceiling panels are not inexpensive. And so you want to work really hard to try to reduce how many you need. And that's why solar control matters. That's why a good envelope matters, is that we can reduce that cooling load to nearly just the internal loads from people. So in this case, we were able to actually get the ceiling coverage down to about 35%, 40% of the ceiling as radiant panels, which is pretty good. I think a lot of projects typically land around 60%, and that's a lot of ceiling, and it's a lot of cost. And so to keep the cost down, we want a really good envelope, really good solar control. Other things that start to make radiant ceiling projects really complicated is they take up ceiling space. Shocking, I know. But there's a whole lot of other stuff that wants to be in the ceiling for a project like this. So we have the radiant ceiling panels. I'm going to talk a little bit about why we want to use ceiling fans always when we use radiant ceiling panels. They're like best friends. Every time you put one in, you should have the other. They work really well together. But in a classroom, you also have projectors. We have supply air vents. We have wireless access points, the little Wi-Fi boxes, fire sprinklers, strobe lights, enhanced audio speakers, daylight sensors, occupancy sensors. There's a whole bunch of stuff up in that ceiling, and it becomes probably one of the most complicated coordination items on a project like this is actually the ceiling. Which is the drawing most people don't care about. The RCP is not typically a compelling drawing on projects, but it certainly is for radiant ceiling. Because it's not just about, so here's a section through one of those spaces, or our early concept section, but it's not just about locating the pieces and plan, but also in seismic country, making sure that anything isn't going to strike any other elements. So the radiant ceiling panels, you can kind of see in that bluish purple color. Those are embedded in the ceiling system, in the drop ceiling. But then we have projectors, we have up-down light fixtures, so pendant light fixtures that have to be able to swing in an earthquake, and then the ceiling fans. And those also need to be either braced or allowed to swing without obstructions. So there's a lot of stuff that goes into a building like this in order to make it effectively work, and also to get the benefits of the ceiling fans. So here's just an image from one of our early coordination meetings for that project, of just showing that none of these things had been really coordinated with each other. So you'll notice here the little spider spider mounts for the projectors are like right above a ceiling fan and supposed to project. The projector is supposed to mount there and project onto this wall. Well, there's a ceiling fan right there, and so you're going to have a projector projecting through a ceiling fan and getting like a disco strobe for lecture, which might make lecture more entertaining, but probably far less effective. So these are the sort of coordination renderings that we do just to start making sure that all the systems work well. And before I leave this project, I just want to talk about the benefits of ceiling fans and radiant ceiling systems. Typically, one of the really exciting parts about ceiling fans is that they can give you a sense of enhanced comfort even at elevated temperatures. So for this project at UC Davis, we're not going to provide air conditioning with the radiant ceilings until the space hits 78 degrees. But the ceiling fans are going to turn on slowly when the space is at 74, 75 degrees. And then they will slowly speed up until we get to 78, at which point the radiant ceiling will start to chill the ceiling and provide additional cooling for above that set point. So these two systems work really well because you can actually make the radiant ceiling system is more effective the warmer the air temp is in the space, and you can allow that temperature to go up and still be comfortable when you add ceiling fans. So again, each of these decisions, when we look at innovations in mechanical systems, we're trying to think about all these systems, how they work together, and how we can increase each other's performance when we add things together. Okay, so I'm going to move into one of my favorite areas. If you hadn't noticed, I love energy recovery. On our DC water projects, energy recovery from the sewage lines, which is super gross, but awesome. I love energy and heat recovery in all of its forms. And if you think about it, it really makes sense. We talk a lot about recycling in sort of life, and we have recycling, compost, and trash bins, and hopefully the recycling bin is really large. Actually, hopefully you aren't using anything, but if you have to, that it's recyclable or reusable. The same way we use that for materials, we should really think about doing the same thing with energy. So we put a lot of effort into making spaces warm or cool to be comfortable. But when we exhaust air out of a building or exhaust anything out of the building, waste or air, it's taking a lot of energy with us. So we want to look at strategies to actually reclaim that energy and recycle it to provide benefit within the building. So the first example is something that is rapidly becoming normal in construction. When I was in school, nobody used these, and now almost every project I have has one. So this is called a heat recovery ventilator, and what it includes is a counterflow heat exchanger. So this can be made out of metal, it can be made out of thin film, and some of them are even made out of paper. But the idea is that we have two airflows. You have the air that you're pulling out of a building, and that has some energy. It's either cool or it's hot, depending on the season. You're pulling that air out of your building, it goes through this heat exchanger, and then it is exhausted out. Meanwhile, fresh new air is coming in at the same time and passing through the other half of that heat exchanger. So those two paths, the two air streams never touch, but they go right next to each other. And so if the outside air is really cold, it will get warmed up by your exhaust air. So your new fresh air will steal some heat from your exhaust air, and it will come into your space relatively normal temp, so close to room temp. Vice versa, if you live in Florida and you're exhausting air-conditioned air, you know, it's 70 degrees inside, but outside it might be 90 degrees with lots of humidity. These systems can also pre-cool air. So your hot, humid air coming in will pass through here and get pre-cooled by your exhaust air. Again, saving energy on your air conditioning load, but still providing exceptional fresh air. Here's a kind of a blow up of that system so you can start to see some of those air channels in each direction. So again, the air streams never touch, but they pass right by each other. And this is a really great strategy on all air systems. So Gail last week talked about variable VAV systems, variable air volume, and constant air volume systems, CAVs. Those all have some portion of air that's always getting exhausted out of the building. And so adding a heat recovery ventilator section or heat core, if you will, to that section can really increase the efficiency of the building, especially in more extreme climates. Now, all of that conversation was just talking about sensible heat, so the temperature, the air temperature that you can feel. But I know all of your minds were thinking about latent heat, and no, this is not an image of me steaming a poor child's head over like a cooker, but it's about the moisture. In this case, an evaporative cooler. That moisture content has a lot of energy. And especially when we talk about Florida, as an example, it's very humid air outside, and you don't want to bring humid air into a building because it'll increase your air conditioning loads. You have to remove that air or else people get all clammy and gross and sticky. So enter what we call an energy recovery ventilator. So before we were just talking about heat recovery ventilator, well, we also have an energy recovery ventilator that can do both sensible and latent heat transfer. So often these take the shape of what we call a desiccant wheel. So this little wheel in the middle is slowly spinning. And that wheel has a salt solution in it. It's a granular salt, a salt powder. But that salt loves moisture. And so as moist air passes over it, through it, it actually wrings out the moisture and absorbs it. And then as that desiccant moves to the other airstream, where say you have hot air leaving the building, it will actually dry that desiccant out. And so the moisture will transfer to the outgoing airstream. These can be used for energy recovery, heat recovery, or both, depending on the velocity that you turn that wheel. So the faster the velocity, faster that wheel moves, the less moisture it removes, but the more heat it will transfer to the other airstream. Now, there's a whole lot of other ways that you use water or use energy in buildings. One of them, we talked a little bit at DC Water, where I said, you know, sewage takes care of a lot of waste. Well, even at small scale buildings, so like your apartment, there's a lot of energy that goes down the drain. So if you think about taking a shower, you've got 104-degree water coming off of your tap. or out of your shower head. After it covers you, you soap up everything. It usually leaves the shower in the sort of 80-degree range, 75, 80-degree range. Well, that's still a lot of energy compared to water coming out of the ground, which is often 55 degrees and lower. So in a really cold climate, the incoming water temperature might actually be closer to 38 degrees, 40 degrees, 44. And that is a lot of energy to actually heat that water up. So there are systems out there that will actually let you take that cold water and they run your drain water in piping around that and actually preheat your incoming water into your building. So a really effective way to reclaim some of that heat leaving your building. There are also fancier systems. This system on the right is from Nexus, and they may or may not be on the market yet. I can't remember. But they do this. It's a very similar system to what we did at DC Water, is they actually take all of your waste, so toilet waste, shower waste, everything, and they can either go through just a dedicated water treatment system, or they can, if you aggregate your loads out with just gray water, they can do heat recovery off of that as well. And so they actually have their water heater uses heat recovery off of that sort of stored water system. So another really exciting idea. So in every project, I would challenge you to actually look around look around your project and identify areas that you think you might have waste heat or waste energy. So a really good example is from grocery stores. All those cooling racks and cooling and frozen food sections, there's a system there making those spaces cold, which means they're rejecting heat somewhere, and usually it's outside. So in one of these systems, and this is a very similar diagram to the heat pump diagram that Gail showed on Monday, one of these ideas is that before, these systems are trying to make areas really cold. So the evaporator is trying to make your refrigerator very cold. That warmer fluid comes in, hits the compressor. The compressor obviously compresses it against your expansion valve. So this section at the top is very warm, and normally that heat is wasted. Well, on a really good project, you would add a little heat exchanger there before the condenser line and pull some of that heat off. And you could use that heat to preheat domestic hot water. Kitchens and restaurants use a lot of domestic hot water. And so you could actually use the refrigerators to help heat the hot water, which sounds counterintuitive, but works really well. But every project often has some sort of waste energy that we can recapture for really valuable reason. So another example is systems where, cooling towers that Gail talked about on Monday, they're designed literally to dump heat into the atmosphere using evaporation and sensible air. So that's a lot of heat that could be doing something else. And so if there is a load on your project where you're trying to heat anything, my first step would be to look at your building and see where we could steal that heat from first before we use a whole nother system to generate that heat. So one example is using waste heat through small engines. So there's actually a little heat engines or adiabatic engines that actually will take waste heat and use that thermodynamic difference in temperatures to actually drive a piston system. And you can actually produce electricity based off of waste heat systems. So these are called Stirling engines. It's sort of the generic name, named after the engineer who invented them. But if you're working on a project that has really high industrial heat, and you're just sending that out into the atmosphere as waste, it would be a really great opportunity to add a Stirling engine for heat recovery. Really effective and relatively low cost. All right, so energy recovery doesn't just have to be a passive thing. Like, it doesn't have to be something that we're just doing because it's a good idea. If you actually combine these systems together, you can actually do what we would call an adiabatic cooling system, or a solar-driven air conditioner. So this is going to take just a couple minutes to walk through, but it's one of my favorite sort of conceptual ideas. I didn't invent this, by the way, obviously, but the idea is that if you actually combine a enthalpy wheel, or the energy recovery wheel, with a heat recovery wheel, you can do you can combine those two things and actually do some pretty amazing things with solar air conditioning. So compressor-free cooling. So I'm going to walk you through a little bit of this. So let's start inside the building, where you're exhausting sort of warm, humid air. So this is all the air that we're giving off, sort of moisture from our bodies. That air is leaving, getting sucked out. So you follow this line to the left. The first step is you're going to humidify that air. So evaporative cooler, that first thing I talked about today, add as much moisture to that air as you possibly can. So it's going to be like really wet, cold air, or cool air. So you're going to cool it down, but it's really moist. And then it's going to go through a heat recovery section. So this is just the sensible load. That now cold air is going to, as it moves through the heat exchanger, it's going to warm up, and simultaneously on that bottom line, it's going to be cooling that airstream down. So as we go back up to the top, as I go from 7 to 8, the air has warmed back up. So now it's sort of neutral air, pretty moist. Then I would pass it through a solar heater where I make it really warm. And so when I make something really warm, its relative humidity is going to drop because I've changed its temperature, but I haven't changed the actual moisture in the air. So now it's hot air, but relatively dry. And it's going to pass through an energy recovery wheel. From 9 to 10, that is drying out the wheel. So the air coming out now is hot and moist. But as I'm drying out the desiccant in this wheel, that means the incoming fresh air, so item 1, the incoming fresh air will actually get dehumidified in step 1, from 1 to 2. From 2 to 3, it's getting cooled down by that heat recovery exchanger. So now it is dry, cool air. I can add a little bit of humidity back to it to make it even cooler, and then to make it as cool as possible. And then if I heat it up a little bit, it's going to be now still, it won't be cold, but it'll be cool, relatively dry air. So in this cycle, with no compressor, no heat pump, you could actually design a system to provide relatively cool, dry air driven by solar only. So here's what that system looks like in an actual box that you can buy and stick on your building. But all of those pieces go in together. Again, no compressor, so very low energy. Really, there's only 3 things that are used, or 4 things that are using energy. There's 2 fans, which your building has anyway. There's 2 little motors that turn the heat wheel and the desiccant wheel. And then there's a little pump that drives water into the evaporative cooling sections. So very, very low energy compared to a traditional air conditioner. If you take these ideas sort of to the extreme, this is one of my favorite products that goes into apartments. It's not available in the US, but I'm working with a team at LBNL to actually design a new version of this for the US market. But this is from a company in Denmark called Nelan. And it's a whole house ventilation system that is using heat recovery that we just talked about, but it's also using a heat pump with that heat recovery to actually heat your domestic hot water. So it's a little complicated, but the idea is that air that's being pulled out of your building first goes through a heat recovery plate to preheat your outside air. So it's stealing a little heat there. And then we have an evaporator coil located in that airstream to steal even more heat out of the air to heat your domestic hot water with the heat pump. So really effective system. It can do dehumidification, ventilation, heat recovery, sort of all the bells and whistles that I like in a mechanical system, especially for a home. The nice thing is, if you need warm air into your house, it can actually steal that air, and instead of heating your hot water at the same time, it can actually heat the incoming supply air. So it can provide some space heating to your room. It can either do that, or it can reverse and actually provide you with air conditioning, cool air into your room. And by air conditioning your room, at the same time, it can use that heat that it's stealing from the ventilation air to actually heat your domestic hot water. So these are sort of very complex diagrams in terms of piping and airflow. But the idea is that no matter what the condition is, the system is looking for sources for waste heat, whether it's trying to steal it from the air or dump heat into airstream in the option of providing space heating. So a really effective system overall. I think Gail on Monday talked about coefficient of performance, or sort of how much energy it takes to move energy on your project. Heat pumps are often around 3, a COP of 3, which means they can move 3 times as much energy from one location to the next as it takes electricity to drive them. And last week I talked about the wastewater heat pump systems can get COPs of 5 or 6. Likewise, this system, because it's looking for really good salvaged heat, it typically gets COPs about 4.5, which is 4.5 to 5, which is still far better than anything you would get from a traditional air conditioning or a heat pump heater. So in a similar way to that system, when we're looking for great places to get energy and to dump energy. So the question came up on Monday about ground source heat pumps. Ground source heat pumps are different than geothermal energy. And I want to be really clear about that. So people often call the systems geothermal, but true geothermal systems are actually more like the geyser, like going down to the deep core, getting heat and having it drive a steam generator. And so there are geothermal energy plants. There's actually one here in California, or a couple here in California, but like Wyoming has a number of them, Montana. Everywhere that you have a lot of geysers or heat, sort of core-driven heat systems, those are great areas, hot springs, good areas for geothermal, traditional geothermal. Ground source heat pumps actually instead just bury tubes in the ground and use it as a place to store energy or extract energy. And so you have a traditional heat pump, but instead of the little coil that Gail talked about on Monday with the fan driving over it, we just bury the coil. Like the whole coil gets much larger and we put it in the ground. And so a ground source heat pump system can run fluid through those tubes. It comes back up around 55 degrees, and then the heat pump itself can actually make either hot or cold water by either extracting heat from that fluid or trying to dump heat into that fluid. So it's not, we're not taking energy from the ground unless we're putting it back at some point. So if you have a ground source heat pump, they work best when over the course of an entire year, your heating loads and your cooling loads are about the same because we're really just using the ground as a battery. If you have too much of a heating load in your building and you're always extracting heat from the ground, eventually you will actually cool the ground down and you'll lose capacity in your system, which is why we don't see a lot of ground source heat pump systems in like Alaska because most of their load is heating load. And so you'd need an enormous field to not degrade the ground temp. So like I said, we're just storing energy one season and then dumping it back in the other. And so you really want those to be balanced, or else you will cause the ground temperature to change. So there's some other sort of exciting systems out there that are a little bit more avant-garde, if you will. GlassX is actually a phase change liquid embedded into a glazing system. So you can see it in the middle of the picture there. That system is actually designed to absorb heat during the day, melt the phase change wax or fluid or into a fluid, and then overnight release that heat into the space as it gels back up. So a means for passive heating and trying to get about a 12-hour temperature swing. So an interesting way to avoid heating energy loads in climates with relatively low sun angles. Here's some images on the far left. the image on the far left is all that phase change material is now warm, so it's absorbed lots of sun, and you can see each of the phases as you go over, as it releases that energy, it sort of recrystallizes and regels up. But the system from GlassX is actually part of a quad pane window system, so 4 panes of glass, and in between 2 of them is that phase change material. And that's on the far inboard side, so the side closest to your room. On the outboard side is actually a prismatic lens that provides both summertime shading embedded in the glass, and in the wintertime allows that sun to go all the way through to strike the phase change material. So that window, it's about 4 inches thick, but it probably costs more than your house, than the house that it's in, but it's a really compelling system for passive heating strategies. Uh-oh, quiz time. So yay, everyone's super excited. I don't know how I always end up with the quizzes in my lecture.
Okay. Stead, if you go one more, there yep. We go. There's the instructions.
So this week, everyone, we're gonna, there's a few more of the questions are multiple choice, so we're gonna give you 14 minutes. I don't know why, I changed it everywhere but here. So ignore the 12, but I changed it in the important places. So once you start, you'll get 14 minutes to complete the quiz. So everyone will have the same amount of time. So even if the quiz isn't locked yet, your time might end if you started it and you've used your 14 minutes. So just give everybody a chance to get over to B course. Log in to week 13, today's date, April 22nd, and you should see the link for quiz 7.
Great, and then we are going to hand over the voice control to Carrie, who will let people know when it's been opened. And again, make sure that don't worry if you get a little bit of a late start. The 14 minutes starts when you start it.
All right, I am going to open up the quiz. The quiz is now open, so go ahead and start taking it. Good luck. We are just waiting for a few people to finish up, so we'll be starting again in a couple minutes. All right, the quiz is now closed, so we can.
Super. Thanks, Carrie. So we'll quickly go over the answers before we jump back into some case studies. So first question, methane it's all of the above. It's bad. It's widely released. It's just bad overall. Load shifting and it's the principle of shifting energy demand to a time during the day when energy is more beneficial to produce. In a VAV system, the load is controlled by changing the air volume. In a displacement ventilation system, the air is applied at the floor level, exhausted the ceiling. That is true. For large buildings, heat is removed by a cooling tower on the roof, which is a component of the refrigeration cycle, and it's most related to the condenser coil. And which of the following is not an example of heat or recovery? Chilled beams. There's no heat recovery going on a chilled beam, but all of those other three options are examples. Okay, so we're going to jump into a couple case studies for the last 15 or 13 minutes or so. So I just want to go through some examples of projects that have used some pretty innovative mechanical systems or even non-traditional mechanical systems to get to really low energy. So this first project is the Hawaii Gateway Energy Center, and it's a science outreach building, a classroom component and a research component. This is a really exciting project because it uses solar energy in a different way. So there's no fans at all to move air in this building, but it uses that large question, or it has that large sort of roof shape that absorbs solar energy and heats air, and it uses that buoyancy of the air that gets hot. That buoyant air wants to drive up, sort of get pulled up, and that's actually going to pull outside air over a cooling coil and then into the space. So it's a displacement type system, but rather than pushing air out of the floor, it's sucking it out of the ceiling and pulling air up through the floor. The other really innovative part of that is actually in the coil. So instead of using a traditional refrigerant, the building is actually using deep ocean water. So it has a pipe that goes out into the ocean and pulls really low level water, almost, over 2,000 feet below the surface water. So the water is very cold. It pulls that water back up and runs it through that coil and then returns it at a higher elevation in the water where it is a little bit warmer. But that really cold water does two things. One, it provides sensible cooling, but you'll notice that it's so cold that it actually water condenses out of the air and drips in, and that water is collected. So really passive system. There's no moving parts except for the one pump to move water through that coil. Here's just a shot inside so you can see those displacement louvers inside for the air that comes through. The one thing is that because it's using that buoyancy system, there are no operable windows in the building. So yes, it's great for cooling, but I think it would be really great is if it were a mixed mode building. And Gail talked a little bit about those on Monday. Another project, this was one that I worked on up in Yosemite, the Yosemite Environment Education Campus. These buildings were actually designed to the Passive House standard, or near Passive House. We did an exceptionally high performance envelope. These walls were almost, I think, 18 inches thick. Lots of insulation. We did heat recovery, so heat recovery ventilators are providing the ventilation air. Detailed thermal bridging modeling to reduce thermal bridges, which meant that we could heat the entire cabin, each one of the cabins of these buildings really efficiently. So here's some of the thermal bridge modeling, again, deciding on which materials to use. Instead of steel, we used wood. Here are the wall systems that we used for that project. Really exciting. We ended up going with the option on the left, which is wood framed, and getting an R value of around R33 for the whole system. So very, very high efficiency. Here's some thermal bridge overlays onto the floor system as well. So again, you can just see the difference between if we had gone with a metal floor frame versus wood. There was a quick question, a couple questions in the chat window. I'll quick catch up. Is methane 1,000 times worse though? Absolutely. Its global warming potential is 1,000 times higher than COP. So it's, yes, it's definitely that bad. And then for the saltwater question relative to the cooling coil, you have to use a you have to use a coil that's titanium. It's designed to allow salt water to go through and the salt water to go back into the ocean. So there really isn't too much of an environmental impact. The actual coil itself is designed for the salt water. The key is when the water goes back into the ocean, you can't take it to the same depth where the water's cold. You want to take it back up so it can be released at the temperature strata that the water is actually at, so that you don't disrupt the ecology in the ocean. And yeah, we can share some of those. I'll see if I can dig up some more resources on that. Just here's some additional thermal bridge modeling from the Yosemite project. Again, trying to isolate this building completely from the very cold exterior. They had over 9,000 heating degree days. So the next project, Exploratorium, which you guys probably know quite well. It was designed by EHCD. The engineers were my former office integral group. And it has a really innovative system that uses bay water for cooling. So it's very similar to the water being pulled in, so salt water. So very similar to the Hawaii project. In this case, it goes through a heat exchanger. So the salt water, it doesn't actually get into the building anywhere, but goes through a heat exchanger and is quite effective. So the bay water temperature is pretty good for most of the year. There are times where there are water source heat pumps that augment that and actually take that cool water and make it even cooler. And there's a lot of systems in the building that are designed to reduce energy. So it's not just the mechanical system, but that's sort of the main thing. Here's a really quick diagram of all the systems that are in there. So it has radiant heating in the slab, and then it has a displacement air system and DOAS system. So it's the dedicated outdoor air system plus radiant. And the air in that system can also be cooled, as I mentioned, from the water source heat pumps using the bay water sort of for free cooling. The building is also mixed mode, so it allows air to move through the building when seasonally appropriate. Here's a little bit of a blow up of that a little bit more. But again, the water source heat pumps are pulling air from the space and then pulling coolness essentially from the bay to provide air conditioning as needed. Much like a cooling tower, the project can actually do what we call water side economizer, which when the heat pumps can turn off, it can just use the bay water directly through the heat exchanger to provide all the cooling. So the heat pumps don't necessarily have to be on, and that makes it even more efficient. So when you can run a cooling tower or a heat exchanger alone with no heat pump, then the efficiency goes up dramatically. This project was a project that I worked on at UC Davis. I've done a lot of projects at UC Davis, kind of strangely over my career, but this is the Jess Jackson Sustainable Winery building. You can actually see it from Interstate 80 if you drive by. It's a pretty small building, but it houses a lot of winemaking equipment. So a lot of water processing and fermentation, not fermentation, but tanks associated with wine production and filtration. Very simple building. It uses displacement ventilation. There is no active heating or cooling. So this building has no heating system or cooling system. It uses an ultra high performance envelope to maintain that interior temperature. And it uses night flush from the ventilation system to cool the building down at night naturally with outside air. And then we've included thermal mass to get that lag. Here's an image of the facade, sort of extreme insulation levels. This is the building going up in construction. Every time a piece of the structure went through the facade, it was thermally broken. So we included these ceramic insulation discs that can take compressive load. So every time one of these outriggers pass through the envelope, say up here, they're thermally broken. So we isolated sort of all the thermal losses as best we could through the building envelope. We did thermal bridge modeling through the materials. We ended up being able to get almost an R56 wall. So this is the wall assembly. So R56 is really, really high. And the roof, we got to near R80. So this was a test example that got us to R75. We ended up getting to about R80 in the final design. So R80 roof, R55 walls, thermal mass. Here's a shot of the inside, so you can see that ductwork as it comes down to the side of the building. You can see it land at the floor, and so those are very low velocity displacement diffusers. The idea is that we use outside air at night to cool all of that mass, and then through the day it can just ride out. And it's very effective at keeping the temperature really steady. So this is actually data from inside the building. So again, no air conditioning in Davis, where outside temperatures regularly in the summer get over 100 degrees. So this blue line, you can see the outside air temperature. It goes all the way down into the 60s and low 60s and mid 50s at night, and then up to 100 degrees during the day. So we take in air at night, cool the building down, and then let it ride. The red temperature is just the inside air temperature. So you can see with no active air conditioning, we were able to maintain this building around 75 degrees year round. And this is just jumps in and showing you that we start that outside purge cycle around midnight, but we could wait until 6 a.m. during a really cold period if we wanted to run the fans less. So really simple building, not much to it, but extremely low energy. We were tasked with designing the building with no air conditioning in Davis, which is pretty amazing. So the last project I'll do for this last minute is actually in South Africa. And the reason I bring it up is because it's a really elegant use of structural systems as a mechanical system effectively. So this is an environmental center at a national park, and the buildings used vernacular forms and combined with a really unique structural system that John Oschendorf at MIT developed. And it uses essentially a play on Gustavino vaults, so load-bearing compressive, 100% compressive vaults that can take a tremendous amount of mass but are very low weight. They're made by these thin clay tiles that can be made on site from soil. So here's the team actually doing training on site with this small hand compressor to make these tiles. The tiles are then shaped into a shape, and then you can see these vaults sort of play out. Very easy to form. There's not a whole lot of formwork. You can see that just a very simple arch framework just to guide the shape, but can take impressive load. And then here you can see the thermal mass being added. So local stone being able to be added to the vaults to carry all that load, but also give a ton of thermal mass. In the chamber down here at the bottom, you can see this is where there's water held. So they're combining thermal mass with evaporative cooling to effectively provide space conditioning and shelter from the sun year round. So not only is the structural system really elegant in itself, it's also in effect becomes the mechanical system by sheltering from the sun and providing nighttime thermal mass to cool at night and keep the space cool during the day. So I think that's it for the lecture. And I think a couple questions came up on the from the quiz. We'll send out some more information if need be. But overall, thank you guys, everyone, for attending. And we look forward to talking with you guys in section.
Thank you.
Thanks, everyone.